All right, so this is chapter 3, which is going to get us kind of really starting down the road that we need to be heading down to understand statistical probabilities and things like that. So it's going to introduce us to a number of different measures. Okay, so it's going to start with what they call measures of location in this book. And again, you've heard of a lot of these, so hopefully we can go through them pretty quickly. But those measures of location are mean, median, mode, the weighted mean, the geometric mean, percentiles, and quartiles. So they're all listed there. You probably learned about percentiles and quartiles in grade school, maybe even like reviewed it again in high school, but you don't use it a lot. If you took the ASVAB test, your grades reported as a percentile, right? But other than that, we just don't use them a lot outside of the statistical world. So the mean, we all know, is like the average as we know it. And so part of the reason I wanted to include these slides is because they show the formulas, and all these formulas are summarized in your book as well. In fact, at the end of the chapter, there's a summary of all the formulas if you need them. But mostly I want to demystify the formulas because they look scary because they use, Greek letters and all sorts of stuff. So you know what the mean is. The mean is just the average. It's like adding everything up and then dividing it by the number that there are. Okay. So this little symbol is called X bar, X with the bar above it. Okay. It represents sample mean. Forevermore, you'll see it in your book says that sample mean is X bar. And then this is a capital epsilon, Greek letter, and it means the sum of. Right, you probably see that as sum, like when you go to click on the sum in Excel, that's what it looks like. And so I want to demystify the formula by saying all this means is the sum of x to the I, or not to the I, but xi means all values of x divided by n, which is the number of observations in the sample. So like, as we start to be able to be not as freaked out by looking at the formula, it becomes really easy to use Excel and other things a lot of times because you're like, oh, I know what that means. This means the sum of all of the values divided by the number of values that are there, the number of observations and also the sample. So they want to differentiate the sample mean. So when we have, a sample meaning we're taking a group out of a larger population from a population mean. And so again, sometimes populations are just too large for us to find the mean age of everybody in the United States would be really difficult. But we could take a sample of 1,000 people and find their age, and that would be different. So, or easier, I guess. So there's the formula for sample mean, and then the population mean. If you look at the formula, it's actually the exact same. It's just the sum of all of the values divided by the number of observations of the population. The only thing different is instead of X bar, it uses the Greek letter mu to represent the population mean. Okay, so it's kind of getting used to those things. So here's a really quick example. I know that you guys know how to find mean already, so I won't spend a lot of time on it. But we want to figure out the average or mean monthly starting salaries of 12 business school graduates. So there they all are with their salaries. All we do is add them all up, divide by the number 12, and we get the mean, right? We know how to do that. Pretty easy. The median is the middle point in a series of observations. So when we have an odd number, it's easy. We just take the one in the middle. So if there's 7 observations, we list them in order. Step 1, right? And then we take, so there's 3 lower and 3 higher, and the one in the middle is our median. We have an even number, then we take the 2 in the middle and we average them. Okay. So that's how we find the median. So here's our example, monthly starting salary. Because this data set has 1, 2, 3, 4, 5, 6, 12 items. We list them in order. We take the 2 in the middle, divide by 2, and that's how we find the median. Piece of cake. And then the mode is the item that appears the most often. Okay. So 5880 appears twice, everything else only appears once, that's the mode. This is way easier right here. So this is the Excel functions for mean, median, and mode. Again, this is in the textbook. You could also take a picture of it if it's better for you. But for some reason, Excel doesn't use the word mean, it uses the word average. So you go equals, average, and then you just highlight the data and it'll find the average, the mean for you. Okay. So just so you know, from an Excel standpoint, average equals mean. But for median, you can do median, and then for mode, you have to do mode.sngl. There's also another mode for if there's multiple modes. Okay. All right. Oh, did you get that? So the weighted means a little different. Sometimes we have data sets that require weights. Think, for example, of your GPA. You might have, let's say you've taken 20 classes at this point. W9, W60, just about that, right? With the and of those 20, 17 of them were A's, and 2 of them were B's, and 1 was a C, or something like that. So to find your weighted average, you have to take, that an A is worth 4 points, you do 17 times 4, and a B is worth 3 points, so you do 2 times 3, and a C is worth 1 point, so you do 1 times 1. Then you add up all of those and divide by the total of 20. Okay, that's a weighted mean. So again, try to demystify what all that means. It's the sum of the weight of a value times the value of the observation divided by the sum of the weights. That's all that means. Okay, even though it looks scary because it's got Greek letters. Right? The Greek people aren't scary. They do make good salad dressing. All right, and you ever seen a big fat Greek wedding? They also use Windex. I don't think that's real. That's just their weird dad. All right. So here's our weighted mean. Consider the following sample: 5 purchases of raw material over a period of 3 months. So we have our cost per pound and the number of pounds. So to find the weighted average, right, we would just take the cost, which is our value of X, the number of pounds, which is our weight, multiply those, so that's W times X. Then we take the sum of W times X, which is all of these, divided by the sum of our weights, which is the sum of those, and that gives us a weighted mean. So that helps us say that our sample mean is $2.96 cost per pound. Okay, if we didn't weight that, if we equally weighted that, we would come out with 307. So if we eat, what I mean by equally weighted it is if we just took all those divided by 5, assuming that's 2.5. I'm assuming there must be an error in the slide, but we took all those divided by 5, we would come out with 307, which, you're not way off. You're talking 4, 7, 11 cents. Although 11 cents out of $3 is 2.5%, 3%, which could matter for some estimations, right? All right, the geometric mean is kind of a specialized thing that I never used ever in real life. I use weighted means all the time, but it's funny how you'll see there's a lot of statistical tools. There's like the ones you'll actually use, like for my business or for my job here at the college. And then there's the ones you never use just because of the nature of what you do. And so you forget how to do the ones you don't ever use. And when you put it called upon, you have to be like, oh, I'll Google it, right? It's okay. This is why for this class, I allow you to use the pages of 2 pages, front and back page of notes for the exams, because never in real life are you called upon to do statistics where it's like, you're not like, crawling through the Mojave Desert and you're like, I need to figure out the standard deviation. Like, it doesn't work that way. You always have a computer with you. So notes are okay. All right, so geometric mean, again, so I love their description. It's calculated by finding the nth root of the product of n values. And you're like, oh, well, that's satisfied with n here, right? I swear the people who write these books, like, they're really smart, but they're morons simultaneously. Like, they don't realize that a human being has to understand what they're trying to do. But what's more important is what it's used for. for analyzing growth rates in financial data, and really use anytime we're looking at changes in things. Okay, that's when we use geometric mean. So here's the formula. Looks a little scary, but it's just you take each value. So a lot of times you'll see this nomenclature, x1, x2, dot, 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 xn. That just means all values in the set, okay, all the way to the last one. And then to the nth root of that. Or you could write it as each of those times each other, to 1 over n. Okay. So here we want to measure this change or this growth in a mutual fund's returns. So we take those growth factors. Again, those are given to us in this case. We weren't able to calculate that from what it gave us. Don't think that this would have had to be given to us. And we just, if there's 10 of them, we multiply all 10 of them by each other and then take the 10th root of it. And that gives us an average of 1.029 or a 2.9% growth rate. Don't worry too much about it, other than maybe be able to calculate it, okay? Which is actually pretty easy. You just take the number of items, you take all the items in the data set, you multiply them by each other, and then you take the nth root, if there's 10 of them, take the 10th root, if there's 5 of them, you take the 5th root, etc. Okay, again, it seems hard, except with a calculator to do all that work for you. You can also use Excel, equals geomean, highlight the data. Isn't Excel wonderful? Kiss those Excel engineers on the mouth. I wouldn't, but you could. All right. All right, so a percentile. Do you guys remember learning about percentiles? I mentioned that you probably learned about it in school, but everybody looked at me like, I don't think I did. No. So a percentile is in essence where we are looking at a certain point within a data set and saying, you say what point in the data set is equal to or greater than 30%, that'd be the 30th percentile, or 75%, that'd be the 75th percentile, okay? And so it's a valuable way of sort of saying, where does a person lie in the data set? That's why the ASVAB score, I was mentioning the ASVAB, you guys probably had to take that your junior year in high school. It was like the military exam. They give you their scores in percentiles. So if you get like a 90 on the ASVAB, it means you scored as good or better than 90% of the people who took it. Which, since it's a national test, that'd be pretty good, right? That means you're in the top 10% of people who took it. So that's kind of what a percentile is. And so you can think of all these applications for it. Saying it just helps us kind of rank things and say, where does this fit into a larger data set? Okay. So to compute a given percentile, we take P, which is the percentile we're trying to calculate, divided by 100 times n plus 1, where n, so just so you know, in statistics, n is always the number of data points in a sample or in a population. Usually big N will represent a population of little n. So if there's 20 items that you're comparing, n would equal 20. Okay. So to find the 80th percentile, so here we have a list of all these, things. This is what, it's the monthly starting salary, back to the same example. So to find the 80th percentile, we're going to take P divided by 100 times n plus 1. So 80 divided by 100 is 0.8 times 12 plus 1, which is 13, gives us 10.4. And then, this is kind of weird, it's what we're calculating is the place, so 10.4. And so with this, we're going to count. Okay, are these in order? Not really. Usually I would put them in order. You just count down and be like, it's somewhere between the 10th and 11th value in order. 1. So the highest would be 1. So again, I don't know why they didn't do that. You would usually arrange them in order, count down and say it's between the 10th and 11th. You find the 10th, 6,050. I should say you find it up at the way from the bottom. So it's the 10th highest. plus 0.4 times the difference between the 10th and 11th. And that's how you find the percentile. Don't worry too much about it because there's an Excel function that will do it for you, okay? But that's how you would do it by hand if you had to. So what that means is at least 80% of the items have a value of 6,082 or less. And at least 20% are that or more. Quartiles are just the 25th percentile, the 50th percentile, and the 75th percentile. So sometimes you'll see them break data into quartiles. Again, as a valuable way of saying, as a quick reference, when I'm looking at a given value, where does that fit? Am I in the lowest quarter, the middle low quarter, the middle high quarter, or the highest quarter of the data? It can be really useful when you're comparing like production line things. You know, for example, if you're producing boxes of cereal and they're supposed to weigh, I don't know, 10 ounces. Well, as they run off, you're taking samples and being like, well, this one's a 9.8, this one's 10.1. And as long as it's within that middle quartile, a lot of times they'll say it's good, you know. But if I'm getting outside of that, the first or fourth quartile, then I know that I'm out of control, it's called. Like, you're out of control, but it means the system isn't working the way it should when they have to adjust the parameters. So it's used a lot in that type of an application. So to find our third quartile, again, we just do the same thing, 75 by 100, 0.75 times 12, which is the n plus 1, gives us 9.75. So we count up to the 9th place, 5950, plus 0.75 of the difference between the 9th and 10th place. Okay. We can use Excel's function. We do percentile.exe, highlight the data range, and then you put in, it says p divided by 100. You get used to most things in just are always the decimal version. So if I wanted the 80th, I just put 0.8. Okay. But that's all. So that's how you do it. If you want to find the 80th percentile, you highlight the data set. You put equals percentile.exe, open parenthesis, highlight the data range, comma, 0.8. And boom, will give you the number. Okay. And then for quartiles, you can either do array. The array is highlighting the data set. Again, I don't know why sometimes Excel tells you data array or data range, and sometimes it calls you array. It's the same thing. Okay. And then comma quart. You could also do it by doing percentile, doing 0.25, 0.5, 0.75, right? That just gives you the quartiles. All right. So there they give you some examples of them. There they did the percentile, here they did the quartiles. And it says when you're using the function, it's not necessary to put the data in ascending order. If you were doing it by hand or by eye, or if you want to call it, it would be nice to put the data in ascending order so you can count the positions up. But Excel doesn't need you to do that. It's smarter than us, right? The AI is going to take us over. All right. So that was all the same types of measures, okay? Which sort of tell us like the measure of, we look at the data set, the way its mean and its central point is, and then where things fall within the data set. So the second type of measures now that we're going to look at is what's called measures of variability. So now instead of just saying where does a given piece of data fall within a data set, or what's the middle point of the data set, or what's the average of the data set, now we're going to say how variable is our data set. Because if you think about it, some data sets have a huge amount of variability or dispersion, meaning, you know, they run from 1 to 1,000,000. And so that would be really variable. Others might, you know, your grade point average can only be between 0 and 4. So it's not very variable, right? And really, it's not 0, it's not even really an option, right? I mean, in theory, I guess it could be, but not really grade point average of 0. So measures of variability help us to understand how widely spread a data set is, and then where given points within that fall within that spread. So they include I won't read them to you. But there they are. There's the measures of variability. And so we'll get to them. Range, super easy. It's the largest value minus the smallest value. All right, so there you go. So what's the range of this data set? We find the biggest value, 6325, minus the smallest, 5710. And the range is 615. Interquartile range is the range of the middle 50% of the data. So this is valuable when you kind of say, because sometimes we talk of range of things in terms of where is it at? Sensitivity to outliers, or how sensitive a measure is to having, like, say, one really crazy one. Like, let's say all your numbers were packed within like plus or minus 30, and then you had one that was 500 away, right? When you use range, you have to include that one that's 500 away. And so it can look like the range is huge, when really like 99% of the data falls in this tighter range. The range is sensitive to outliers, or the smallest and largest data values. So interquartile range attempts to sort of remove some of that sensitivity by saying, let's see where the middle 50% of the data fall, right? So the first quartile is 0 to 25%, and the fourth quartile is 75 to 100%. So the interquartile range is 25 to 75%. So they find the third quartile, the first quartile, subtract them, and that's our interquartile range. All right, so now the ones that really get used more, like as we move forward, you'll see like all, we're going to use mean a lot moving forward, but not median and mode nearly as much. We're going to use variance and standard deviation, which we'll learn about in a second, a lot moving forward, but not range and interquartile range. So it's an interesting thing. Things like percentiles and quartiles, they get used in some very narrow aspects, not narrow, but just specific aspects, I guess, of statistics. But things like variance and standard deviation and mean, they have very broad application. So variance is the measure of variability. Let's see. So it's based on the difference between the value of each observation, which is X, and the mean of the sample, which is X bar. Or if we have a population, which is the mu, right? So in essence, what we're doing to find our variance is we're just looking at the difference between each data point from the mean. Okay. So here is the formula for variance. Again, don't worry too much about it because there's an Excel function for that. But again, I wanted to. There are times when there won't be an Excel function, and I'll teach you how to create your own calculator in Excel for things. But really, all it boils down to is being able to break down the formula and build your own calculator, right? Which I think sometimes more than learning about all the statistics, learning the ability to be confident in Excel and build a calculator as you need it is like the more important skill. That can be recreated. All right, so the formula is the sum of X, a given data point, minus X bar, which is the mean, squared, divided by n minus 1, where n is the number of items in the data set. And for a population, we have the sum of each item of X minus the population mean over the number of items in the population. Okay. Standard deviation is just the square root of variance. Because here's the problem. The answer we will get with variance will be in squared units. So when we say, oh, how variable is this? And we get this answer, if it's in squared units, it's not very meaningful to us. So if we take the square root of it, it puts it back into the base units we were using for the mean and everything else. So it's more comparable. So standard deviation ends up getting used all the time. So I'll use and there's the formula, the square root of variance. Okay. It's interesting that variance is S squared, and standard deviation is S, right? Because the square root is squared. All right, so here's our variance and standard deviation function. VAR.S, that's sample variance. STDEV.S, sample standard deviation. If you need to do it for a population, VAR.P and STDEV.P. Okay, again, summarized in your book. If you need to, look back and remember. All right. Well, like I said, you guys know, the drill by now, which is like, I'm going to dump all this info on you, and then we'll work through some problems next time we meet. So you don't have to worry about memorizing all this. Just try to sort of think about what it means. Okay. The coefficient of variation indicates how large the standard deviation is in relation to the mean. So all we do is take the standard deviation, divide it by the mean, and then times 100. That's the coefficient of variation. Again, it helps us see like how variable a data set is relative to its mean. Okay. All right, so back to our example, our monthly starting salary, which should give us more detail here, but I guess they kind of summarize it on one slide. What we would do is take each of those items, it's the sum of each of the items minus the mean squared over n minus 1. So we end up with 27,440.91. The standard deviation is the square root of that, 165. The coefficient of variation is 4.2%. So I'm giving you all this info, but without context, it's not super helpful. Okay. So I'm hoping today is like here's all these things, and then Friday will be like, here's how we use them a little bit more. Okay. So there they just show cell being used. Mean, median, mode, variance, standard deviation, and all that's given to you. Again, I don't use variance that often. I just use standard deviation, but some, if I know, the thing is, it's like one's just the square of the other. And so if I know one, then I can figure out the other, right? Standard deviation is meaningful because it's in normal or standard units. So here's what this means a little bit. We're saying, so here's our monthly starting salaries. The mean or average of that is $5,940. So this was, what were they, students just graduating? I forget what it was, but their average starting salary. So on average, they're making $5,940. And then the standard deviation of that is $165.65. So and then remember we figured our coefficient of variation was 4.2%. So what that means is that's not a terribly widely spread out set of data, right? Like, and we could have told that even from the beginning, from like our range. It only goes, what was it? 6,300 down to 50, whatever it was. And so, really just plus or minus $1,000 or so covers what everybody's making. That might be different for different types of jobs. What if I said, what's the average salary of someone without a college degree 10 years after graduation? That would probably run the gamut from people still working in fast food to someone running heavy equipment up at the mine making $100 grand a year. Whereas teachers' salaries, we would expect, would have actually a narrower. By going to college and getting your teaching degree, you're going to be working as a teacher, which means you're going to be making somewhere between 38 and 48,000 probably. You know what I'm saying? And so that's the value of this, is we could look at two data sets and say, oh, this one's a much wider. So that way, when someone tries to say you don't have to go to college, which is true, and I know a guy who didn't go to college and he's making $100 grand a year, and you're a teacher and you're only making 40, you can be like, well, that's true, but 92% of people that didn't go to college are not making that, right? This guy's, there's a lot more variability. And so sometimes education, as an example, buys us consistency or steadiness more than it buys us a guaranteed, anything, or whatever. Like that's the value of this type of data. Which brings us to z-scores. So a z-score is a standard score, or sometimes they call it a standardized value or something. And it lets us know the number of standard deviation a given point of data is from the mean. So You can calculate it by taking the data point minus the mean, sample mean, divided by the standard deviation. Okay. Or you can use Excel's standardized, so equals standardized, and you put in the number, and it will give you the z-score. So here's our class size data. Looks like they looked at 5 different classes, counted the number of students in the class, found the mean. So by taking all these, adding them up, dividing by 5, the mean is 44, and then calculating the standard deviation, which is 8. So then you can calculate the z-score of each of these, which is, let's see, 0.25, 1.25, negative 0.25, etc. So a z-score is always in, so just the units of a z-score is in standard deviation, and we'll get more about what a standard deviation is in a second. And it can be, if a z-score is 0, that means the data set exactly hits the mean, or the data point of the data set. If it's positive, that means it's above the mean. So in this case, 46, which is 2 above the mean, has a z-score of 0.25. So it's 2.25 standard deviation higher than the average. Okay. And 54 is 1.25 standard deviations above the average. And 32 is 1.5 standard deviations below the average. Okay. This will make more sense when we start to learn about Chebyshev's theorem, which sounds crazy. You're like some Russian guy. Isn't that the guy that was, let's check off. Okay, Star Trek. So Chebyshev's theorem says at least 1 minus 1 divided by z squared of the items in any data set will be within z standard deviations of the mean, where z is any value greater than 1. Oh, thanks, Chebyshev. Wait, was that Russian? No, that was English. It was just hard to understand. So here's what it really means. And we could calculate all sorts of other ones, but it means at least 75% of all data values must be within 2 standard deviations of the mean. 89% must be within 3 standard deviations of the mean, and 94% must be within 4 standard deviations of the mean. So the value of this is now when we can look at the z-score of a data point and be like, is that normal, or is that way to freak out there an outlier line, right? If something has a z-score greater than 4, you're like, this isn't something I should count on as being standard or normal. It's 96% chance of it not, it's in the, or 94%. It's beyond 94%. So that's really what Chebyshev's theorem means. We could calculate, so suppose the midterm test score of 100 students in the course had a mean of 70 and standard deviation of 5. We want to know the number of students having test scores between 60 and 80. Okay, so we could use Chebyshev's theorem. And so we do 60, 70 minus 2 times the standard deviation, 70 plus 2 times the standard deviation gives us 75% of students fall between 60 and 80. So we can use it for that. So that can be valuable. Okay, but its real value usually falls in us going, is this data we're looking at normal? And even more than Chebyshev's for this class, as we move forward into probabilities, we use what's called the empirical rule. So the empirical rule means when we have data that conforms to, this is a bell-shaped distribution, but it's often called a normal distribution, and it looks general or sort of like this. That should just go out, right? Where the mean is here. So when our data conforms to a curve like this, the empirical rule will give us even tighter parameters on how the data will fall. The cool thing about the empirical rule is pretty much if a data set is even a little bit big, we can assume it will conform to the normal curve. All we need is an n, sample size, of 30 or greater, and we can assume that the empirical rule works. So under the empirical rule, approximately 68% of data values will be within plus or minus 1 standard deviation. And 95% will be within plus or minus 2. And 99.7%, so pretty much almost all of the data points will fall within plus or minus 3 standard deviations of the mean. So if we have a large enough sample size, we can assume that this will hold true. And it doesn't have to be a big sample size, which is interesting, 30. Now, the bigger our sample size, the more confidence we'll have. We'll learn about confidence later, but it's kind of an amazing thing. So there's their much better drawn bell-shaped distribution or normal curve, much better than mine. But so what we start to do is we start to say, okay, here's the mean. Here's plus or minus 1 standard deviation, plus or minus 2, plus or minus 3, and it gives us some sense of how normal our data is and where it falls. So an outlier, that means data that we don't want to depend on as being normal or regular, right? Like just because you've met a person with, you know, a 150 IQ, doesn't mean that all people have that. You don't ever worry that like when aliens are going to come to Earth, they're going to be like the stupidest person on Earth and then assume all humans are like that, or vice versa, they'll be like the smartest person on Earth. Or have you ever like been like teaching your dog a trick, and then you realize I have no sense of if this dog is intelligent or stupid by like dog standards, like what's the norm, right? So that's how this kind of gets, you know, it doesn't get used for dogs or for aliens, but the idea of considering what's normal versus what's an outlier. So data with a z-score of less than -3 or greater than +3 is generally considered outlier data. In other words, so far away from the mean that it can't be, it's not super reliable. No, of course, sometimes if we're doing experiments and we're getting results that are consistently 3 points higher than the mean, 3 standard deviations higher than the mean for a certain input, well then of course we're going to look into that, right? We're going to say, well, I'm going to continue with that input. It continuously or consistently produces what seem like outliers, but apparently, you know, so, you know, consider if you're generating electricity and you're trying different conductors and then you try a superconductor cool at just the right temperature, you might realize, oh, what I thought was an outlier is a norm under these conditions. And that's how we do science, right? We recognize, you know, a data set and say, is that truly an outlier, or did we affect the experiment in some way here that's leading to this outlier? Is it replicable, reproducible? One of those things. All right. All right. A couple other measures you'll see in this chapter and that get used, but not a lot for me at least. One's called a 5-number summary. And so if you have a whole data set, like a whole list of numbers, that 5-number summary would include the smallest value in the data set, first quartile, median, which is the second quartile, the third quartile, and the largest value. Again, that nicely, especially let's say you have a huge data set with 1,000 numbers in it, that would nicely summarize that data set, having those 5 numbers. So this one, it's not as necessary when you only have 12 or whatever, but still. So our 5-number summary here would look like this. Again, that gives us a pretty good idea of, well, gives us the high, the low, the middle spot, and the 2 quartiles. Sometimes you'll see a box plot, or sometimes they call these box and whisker plots. Again, this is one of those things I completely forgotten when I was in college math, but like one of my kids showed up with it like in 6th grade homework. So apparently we learned about this at some point. So all a box and whisker plot, or this called it a box plot, shows is it shows this 5-number summary in essence. It shows the lower limit. It shows the first quartile and the third quartile, and the median. And then usually these whiskers will extend to the limit, so I'm not sure what they're doing there. But That's all that is. Okay, it's sort of a graphic representation of that 5-number summary. All right, last set of measures. Measures of association between two variables. So you see two variables and you're like, how related are they? Right? Like an X and a Y variable wrapped in a line plot or something like that. So if you think about a lot of the decisions we make in business have to do with relationships between variables. I ran advertisement and spent this much on advertisement, and my sales were this much. And when I increase my spending on advertisements, does it increase my revenue or does it? Does it not? Right? Things like that. There used to be stories about Thomas Edison, right? Who you guys know who that is? He invented the light bulb. He was known for sort of like just saying like he didn't care about science. He was just like, one way we can figure out like the limits of things is just to keep pushing them further and further until they break. So yeah, there's a story about him testing a rock crushing machine and it was crushing rocks at a certain rate for like, this is like for a mining application, right? And so he comes to his worker and he says, well, can it go faster? And the guy goes, I don't know, we've never tested it. He's like, why haven't we tested it? Well, because it could break. So he's like, well, can you increase the speed of it by 10%? The guy goes, yeah, I've never done it. So do it. So the guy increases it and it works. And then he increases it 10% more and it works. And he increases it 10% more and it works. He increases it 10% more and it completely breaks the thing. And his employee, his worker is like, you just broke the machine. He's like, no, I just got like 35% more output out of the machine. I'll fix it and run it at that speed. And so now, with modern engineering, a lot of times we can use things like SolidWorks. Have you ever used SolidWorks? Which is super cool. It's kind of like a software that lets you build things in virtually and then test them to try to get the maximum amount of output out of something. And then you build a scale model. And then, yeah, my son-in-law and daughter have SolidWorks on their own computer with their 3D printer for 10 years. They just go building stuff. Like when we had COVID, they built me this little connector for like an air bottle that would like, because an air horn is too much when you're rapping, but the air bottle would just go to like my Fox 40 whistle. But I say on that, but they're nerds. Anyway, so this is measures associated with two variables, right? How much do we put into something and what's the output of that and how related are they? So covariance is the first one. So it's the I'll read you the definition, the linear association between two variables. Positive values indicate a positive relationship, meaning as one variable goes up, the other variable goes up. And negative values indicate a negative relationship, meaning as one variable goes up, the other variable goes down. Okay. So here's our formula for covariance. Looks scary, but it's the sum of each value of X minus the mean times each value of Y minus the mean over N, the number of items in the data set minus 1. And for a population, it's pretty much the exact same, except there's no minus 1 on the population. That's because with samples, what we're trying to do is introduce some error into the system because we know it's a sample and doesn't have all the data points. You'll see that over and over. And then the correlation coefficient, I think, is a better and easier way for most applications, although not all, but to see the relationship between two variables. Mostly because, so there we have standard deviation, or the S of X at Y, XY times S times SX times SY. Okay, so I'll just show you the example of why I like correlation coefficient better for me, because I'm not an expert, is that it gives us a value between -1 and +1. And I think that's easier to read. So -1 means there's a strong negative linear relationship, meaning when X goes up, Y goes down. +1's a strong positive linear relationship. When X goes up, Y goes up. And then like 0 would mean like there's probably no relationship between these things. And so to me, that's easier to read. Positive, the closer it gets to 1, the stronger the relationship. The closer it gets to -1, the stronger the negative relationship. And in the middle, the weaker the relationship. That's just more valuable. So here's our example. Stores manager wants to determine the relationship between the number of weekend television commercials shown and the sales of the store the following week. So there's this chart, number of commercials and sales. I mean, a lot of times you're like, is there any relationship between the two things? So here you can see there's the value of X, number of ads, Y, sales. So, and then we found the mean, the bar X, somewhere I didn't tell us it. But so X minus the mean, Y minus the mean of Y, and then multiplied together, divided by n minus 1 gives us a correlation coefficient of 11. Again, what's hard with that is like, I don't know what that means, other than there's some sort of positive relationship between the two. I can calculate the correlation coefficient just by taking 11 times 1.49, or divided by 1.49 times 7.93. I'm not showing where it's all from, and we're trying to go quickly, so we'll do it in an example. And so here, this means something more to me, because this number could also be like 20, and it doesn't necessarily mean any stronger relationship. It's hard to know, but here, if I know 1 is a strong positive correlation, then what I'm seeing is when I run more ads, I get more sales. Then the question is it enough more sales to cover the cost of the ads, right? Does it have to be enough? All right. Again, Excel function equals covariance dot S for example. I let your data X, then Y. And for correlation coefficient, CORREL, same thing. Highlight your data X and Y. And that's it. So I warned you ahead, there's just a ton of stuff in this chapter, but a lot of it's not hard, like mean, median, mode, like that's pretty easy. And there's Excel functions for all of them. There's also a summary of all of these formulas at the end of the chapter, and each of those Excel functions is also spelled out in the chapter. Okay, so Friday we'll actually do a problem together that gives us an example of several of these. So we'll do a few problems for assignment together. All right. I know there's a lot of new stuff. Have a great day. I don't know where all your friends are. Tell them to come to class. All right.
Not my friend.